This question is from Q2017 Mechanical Engineering paper, set 1, question number 37. Two black surfaces AB and BC of length 5 meter and 6 meter respectively are oriented as shown in the figure. Both surfaces extend infinitely into the third dimension. Given that view factor F12 is 0.5, T1 is 800 Kelvin, T2 is 600 Kelvin and T surrounding is 300 Kelvin. And Stephen-Boltzmann constant A is given to be 5.67 into 10 to the power minus 8 watt per meter square Kelvin raised to 4. The heat transfer rate from surface 2 to the surrounding environment is dash kilowatt. Let's find out. So we'll write the given information first. View factor F12 is given to be 0.5. So there are two surfaces 1 and 2. View factor of 1 with respect to 2 is 0.5. Temperature of surface 1 T1 is 800 Kelvin. Of second surface it is 600 Kelvin. For surroundings the temperature is given to be 300 Kelvin. Then Stephen-Boltzmann constant A is 5.67 into 10 to the power minus 8. Having the unit watt per meter square Kelvin raised to 4. Let's give a number to the surroundings also. So let's assume it is number 3. It will be easy to write down the denotions then. And we need to find out the heat let out by surface 2 to the surroundings. So we need to find out Q23, the amount of heat dissipated from surface 2 to the surroundings. The first relationship that we will use is summation of the view factors is 1. So we can write down F21 plus F22 plus F23 is equal to 1. First thing, F22 will be 0 because surface 2 is flat. Now F21 and F23 are the two we need to figure out. So we can use the reciprocity relationship, that is area of surface 1 into F12 is equal to area of surface 2 into F21. Now it is given that the surfaces extend infinitely in the third direction. So we can take 1 meter length in the third direction. And therefore we can write down the area as 6 meter is the length into 1 meter is the width in the transverse direction into F12 is given to be 0.5. Similarly, A2 we can write down 5 into 1 and F21 is the view factor that we don't know. We can find it out using the same relationship. So F21 will be equal to 6 into 0.5 divided by 5, which comes out to be 3 by 5. That is 0.6. Now we know F21, we can substitute it over here and find out F23. So F23 will be equal to 1 minus F21, which is equal to 1 minus 0.6, simply 0.4. We have F23. Now in order to find out Q23, which is the rate of heat transfer from surface 2 to surroundings, that is surface 3, we have to use the formula. Heat transfer Q is equal to Stephen-Boltzmann constant. Generally it is denoted by sigma, but we have used A, so we'll write down A here, small a, into area of surface 2 into F23, that is view factor of surface 2 with respect to the surrounding, into temperature of surface 2 raised to 4. Substituting all the values here, Stephen-Boltzmann constant 5.67 into 10 to the power minus 8. But remember, the unit is watt per meter square Kelvin raised to 4. So remember that we are going to get the heat in watts and then we have to convert it into kilowatt to fill in the answer. Next thing, area of 2. Simply we have discussed this earlier also that 5 meter is the length of the surface into 1 meter is the transverse width we can consider into F23 we found out 0.4 and temperature of surface 2 is given to be 600 Kelvin. So 600 raised to 4. This when calculated in digital calculator gives us Q is equal to 14,696.64 watt. And as I already told you, we need to convert this to kilowatt. Dividing this by 1000, we get 14.696 kilowatt. Or simply we can round it off to 14.67 kilowatt. Let's go back and fill in the answer. So the heat transfer rate from surface 2 to the surrounding is 14.696 kilowatt. To learn more about view factors or per se shape factors, you can refer to the NPTEL video Module 2, Lecture 5, Shape Factor. It's from the course Radiation Heat Transfer. The course is by Professor J. Srinivasan
He is from Department of Atmospheric Sciences of IISc Bangalore. I hope this solution will help you clear your doubt. Thank you.